Well, I am tremendously honored to be given the Dickson Prize. I've known of Carnegie Mellon University for a long time, and I have friends here that I've known over years, from my early days of science up until now. So it means a lot to me to win this for so many different reasons. And the respect I have for this institution also arises from its reputation, which I know across the disciplines, except I just learned about drama today, so that's really great too. So what I want to talk to you about today has to do with water. It's such an amazing substance. The fact that there's something that can break through stone, push stone, strong enough to do that and yet light and airy enough to dance in the wind as a snowflake. The fact that it makes up 70% of the land of water on this planet and is 60 to 70% of our bodies is amazing too. It's such a simple little molecule, 3 atoms. Kind of looks like Mickey Mouse. But don't let its commonplace and simplicity fool you, because scientists have been curious about this molecule for centuries. And it's that curiosity that has led me also to be interested in water. Now, what do we know about water? Well, we know quite a bit about it when it's in this gas phase, when it's just kind of bouncing around. It's actually quite the introvert, just kind of bouncing around up in the air. Quite the introvert. However, when it goes to form a liquid or a solid, it becomes quite the extrovert. It's grabbing onto nearby neighbors in something we as chemists call a hydrogen bond. The rest of you non-scientists may say that it knows how to pull off quite a rave. Being able to dance around and grab onto different partners all at once. Imagine a party where everybody's dancing and they're constantly swapping partners, 3 or 4 at a time. Monogamous, it is not. But in fact, it's that special gregarious properties, that party animal, that gives it such incredibly important characteristics. And also, its ability to do some pretty special things. One of them being its ability to absorb a tremendous amount of heat without its temperature changing very much. I find it absolutely amazing that we can go eat a big full lunch while all kinds of chemical reactions are going on in our bodies, millions of chemical reactions, and we stay around 98.6. And that's because the water is being able to absorb and not change the temperature very much. And in fact, that's why water plays a role in also our atmosphere and around us. But again, there are a lot of mysteries about water that we have yet to understand. And one of those mysteries comes from the surface of water. I'm sure you've all seen stuff float on water. Bugs float on water, leaves float on water. And it's because it has a very high surface tension at the top of that water surface. Trying to understand what's leading to that high surface tension as well as properties of that water surface is what we focus on. So it's a really important surface, not only from a scientific perspective, but when you think about it, everything that gets into our water has to go through a surface, right? So whether it's water going through a pipe, contaminants can have to go through that water surface, or up in the atmosphere, where the atmosphere is made up of a lot of different particles and ice droplets and aerosols. And a lot of those little aerosols or little droplets are chemical factories, and stuff's got to get through that surface before it ends up in there. And also an issue of what happens when you have environmental pollutants even on the ground, that they need to get through that water surface and in areas of environmental remediation. I'm going to give you a couple of stories about 2 of these last ones having to do with research that we've done in the area of atmospheric chemistry and also in environmental remediation. I'll give you those 2 examples of studies today. But measuring that top surface, as Linda noted, measuring the molecules at only the top layer, 1 or 2 angstroms, 1 to 10 angstroms down, so 2 or 3 water molecules, is very, very challenging. Because when you think about it, for example, if you look down on a pool of water and you see yourself reflected, you might think that that reflection is coming just from the top layer of water, but actually it's quite a few water molecules down as the light penetrates down. And so if we're just going to use light as a probe of that surface, then it's going to be tough to figure out how to get that light to only look at that very top layer. And I'll tell you how we do that. But one of the other things and so we do really fancy laser stuff, as I'll tell you about. But the other really important technique that we use is much, much simpler. And that is to be able to do surface tension measurements. So as I said, water has a very high surface tension. And when you put things on that water surface, in general, that causes the surface tension to drop. So as we put more things on the surface tension, this simple dipping a little metal plate and pulling it through that interface, seeing how much tug there is to pull it through that interface, is what we use to measure the surface tension, as well as a pendant drop method also. But I always have to, when I mention this, it reminds me to tell you, especially for the students in the audience, that this was the person who actually did some of the very first surface tension measurements were not some highfalutin scientist somewhere, but actually was Agnes Pockels. Agnes Pockels was a 16 to 18-year-old girl taking care of her parents in Austria back in the 1800s, and she noticed that when she was washing the dishes for her parents in her kitchen, she noticed there was something very interesting about the surface of that water, or how it behaved with different things in the water. So she took a button and she took a string, and she started to do measurements with that surface, that string, and a button. She was so enamored by this, but she couldn't go to college. She couldn't take a lot of science courses because in those days a girl couldn't do that. But her brother could. Her brother was actually a physics major at a university nearby, and so he brought his physics articles home. And so one day, she was taking this data, putting it in what she saw as a notebook, writing up all of this, what she was observing. And then one day she noticed from her brother's journals that actually there was this guy named Rayleigh, and he was doing some stuff like her, not with the button and the string, but in a real laboratory. And so she was so excited about this that she wrote him a long letter, and she sent all of her data to him. And she said, I just hope that this can be helpful to you. Do whatever you want with this data. If it's helpful to you, that would be great. And she heard back from him. In fact, they published a paper together, and he put her name on it because he thought it was so important. So when you're curious about something, follow it. All of us, no matter what it is. So that's my story. And every time I think of those surface tension measurements, you bet I think of Agnes Pockels. But then we get fancier, and those surface tension measurements tell us something about the quantity at the surface, how much stuff is at the surface, but not the molecular nature of it. So in order to do that, we take laser experiments, and in this case what we do is we take a very ultra-fast lasers, put an infrared and a visible beam, and we look at the light that comes off. It's a different color, and that's the sum of the two frequencies. Now, of course, you got a lot of this infrared wonking off of here because this is a really bright beam. And so you filter out this little bit of signal. And that little bit of signal that's created of that color can only happen, as Linda mentioned, when you have broken symmetry. So what's above looks different than below. So you go about 10 angstrom down into the water, and what's above looks the same as below. So you won't get any signal down there. You'll just get it at the surface. This signal is extraordinarily weak. It's extraordinarily weak, so filtering it out and measuring it is hard. However, as I'll show you, once you get near a vibrational mode in the molecule, this signal bumps way up. So what we're doing in these experiments then is we're able to then measure the signature of those molecules at the surface. So again, right at the top layer, about the first 10 angstroms down. And as we know, molecules, they vibrate back and forth, and water is one of those. It's vibrating like this. Okay? And so that has a frequency associated with it, a color of light associated with it. And so when we hit near that frequency with our infrared beam, that otherwise weak signal goes up. So what we're getting and that allows us then to measure a spectrum, which is just intensity as a function of infrared frequency. And so we can pick up water modes, we can pick up a lot of different vibrational modes which are at different frequencies. And so why this is so important for water, because I'm mostly going to focus on water today, is the fact that when water decides to grab on to another water molecule, that frequency changes. So the frequency of one water molecule stuck to another one is going to be different than if it's stuck to two of them. In fact, that vibration is going to slow down a bit. And then if it's 3 and it's 4, that frequency that we measure can tell us something about whether the water is the introvert or whether it's the extrovert. And we can also then determine the orientation of the water molecules at the surface by playing around with polarization. So so that's really important to get the information about how the molecules bond and structure and orient at the surface, and you'll see why that's important. But it doesn't tell us everything, and so what we need to do then is to also do theoretical work coupled with this, and in that case we do a combination of molecular dynamics simulations and density functional theory calculations. And what we do in that case is we actually figure out what all the molecules, this is an interface of, for example, an oil with water. Water is the little red and white buttons. We calculate what each of those water molecules at the surface, how it orients, how it bonds, and then we calculate a spectrum for it, for every single one of them, with DFT, and then we add square and come up with something we can compare with the experiment. And if it compares well, then it gives us a lot of details about what's going on in the system. So we always have to have that double check to make sure that our calculations are going the right direction. Okay, so now some data. So this is a spectrum now of the surface of water, and that we first measured, as well as Ron Shen's group and several other groups now have followed up with that. And let me tell you what this is. In spectroscopic terms, this is a very sharp peak and a very broad blob. We don't always call it a blob. I'll call it for that for now. And so this is now the OH stretching modes of water. And here is where you have very little bonding interactions. This is the introvert, and this is the extrovert of water. Okay? So this very sharp peak is very interesting because what it corresponds to is actually something we call a free OH. And that means, what's that telling us? When you look down at your glass of water, you got about 25% of those water molecules that are doing this. You got one OH staring up at you and the other OH going into the water. And there's a reason why it's such a sharp peak. It's because this one, when it bonds to waters, this one isn't bonded to water. It's uncoupled from one another. So it acts like itself. So it's a signature mode that I'll show you gives us a lot of information. Then when you go a little bit deeper into the spectrum, this is more water that's like in liquid water and ice. Okay? So from a spectrum like this, just a simple spectrum of water at the surface, we've learned a lot, coupled with our computational work, we know a lot about what the surface of that water looks like in very general terms. So we know that that very top layer of water molecules has this, what we call the free OH sticking out into the air. Of course, some of this is evaporating also. And then you have other water molecules that are largely in the plane of the surface like this, about 5 degrees off axis, and they're kind of roaming around like this, but then you've got the ones that are doing this. Then you go about 3 or 4 angstroms down, and they were pretty weakly bonded at the top, but then they get a little stronger, so 2 and 3 water molecule bonding. And then you get to, after about 10 angstroms, water is bulk, everything is completely random. Now, why we don't see it when it's completely random is also because, not only that asymmetry, but we're only going to pick up molecules that have a net orientation. So with this technique, it's not only they have to be at the interface, but they have to have a net orientation. And if they're randomly oriented, they'll cancel each other out. So this one would cancel out something like this. Okay, so that's what we know about the surface of water. And now we're going to take the next step and put something on it and show you what we've learned. So this is the atmosphere, and we used to believe in the olden days, several decades ago, we used to believe that a lot of the chemistry in the atmosphere happened because gas phase molecules were bouncing off one another and there was photochemistry going on. But now we know some of the most important chemistry that happens in the atmosphere. Many of things that are studied here at CMU have to do with little droplets and aerosol particles and dust particles, where a lot of the chemistry happens inside those droplets as well as at the surface. And so but it's a very complex issue to understand what's going on at the surface of these droplets, water droplets, and yet it's critically important to have that information to be able to put big models together that then can predict what behavior is going to happen. So so that's the title of my talk then, do environmentally important molecules surf, sink, or swim on a molecular surface. And I'm going to give you some examples of those. I'm also going to give you a multiple choice exam. And that's just not for the students, that's for everybody. I'm an equal opportunity teacher. Okay, so what I'm going to talk about is some work that we've done with sulfur dioxide. And it does look a little like Mickey Mouse too, but it's a lot more toxic and a lot more pungent. And it comes from a number of different sources. Naturally, it comes from biogenic sources, and it also comes from volcanoes that put out SO2. And then we also have SO2 comes from burning dirty coal, with coal that has sulfur in it. So when it then burns, it oxidizes to produce sulfur dioxide. So that once the sulfur dioxide gets up into the atmosphere, it then undergoes chemistry up in the atmosphere. And that's what we would like to be able to understand, but what happens at the surface, particularly if it goes up, and then can interact with the droplet. So in this case, as I have here, the major source of sulfur dioxide goes up to form, in this case goes up to form sulfuric acid. Once it gets up into the clouds, it oxidizes to form sulfuric acid in various ways, and then it can come down as acid rain, which is not good. Acidifies lakes, kills plants and animals, and fish and so forth. Now, recent studies by Barbara Finlayson Fitz has suggested that actually something's going on when water gets near, when SO2 gets near a water surface. Seems like there's something going on at the surface. And so we wanted to be able to understand what that is going on at the surface. It seemed like a perfect first example of how we might be able to study a gas interacting with the water surface in this way. So what we did then was to, in this case, rather than going up in the atmosphere, to do laboratory experiments where we're now looking at a water surface in the laboratory and then exposing it to sulfur dioxide to see what happens. So the question in these studies is, what role does a water surface play in gaseous uptake? It's multiple choice time. So I'm going to give you 3 options, okay? And then I'm going to show you data. And then we'll vote on which we think is the role of the water surface with sulfur dioxide. So here we go. Number 1, is the surface a doorman? So is the surface just opening up and say, come on in, come on in. Happy to have you here, so it can just dive right in. Or is it the barrier? So the SO2 just kind of bounces off the surface and goes away. Or the temptress, which says, come on in. Water's nice. Come on in, and pulls it in. Okay? There's your 3 options. Okay, so now I'm going to show you the data, and you can figure out which one of these 3 it is. See who's courageous enough to vote. Okay, so what we do, we take this water spectrum and we put SO2 on it, and let's see what happens. As I have here is the water spectrum. Put SO2 on it, and look what you see. You see that this free OH broadens. Again, I told you before, when things bond, kind of push in that water in that direction. Again, this is all water. And then this is ions that are formed. So this free OH broadens, suggesting that actually there's some kind of a complex formed at the surface. Or secondly, increased hydrogen bonding signal in this region, and that has to do with the fact that ions are going into the surface layer. And those ions are breaking up, or changing the water structure, making it stronger, which is there. So it's clear that water is doing something at that surface. And it goes in and forms ions. So is it reversible? Well, let's turn the SO2 off, and what you see when you turn it off is that actually free OH comes back in its normal form. But you still have ions that have gone into solution, and that's what that's telling us. So the SO2 complex formation is reversible, comes on when SO2 is there. It shows it's bonded to water, and then it comes off again. But the uptake is not reversible. Ions go in and they stay there. So then what happens when we cool it down, which are closer to atmospheric conditions? And in that case, what you see now is a function of temperature. And we stop before we form ice, just cold enough before we form ice, because doing the sum frequency experiment off little ice things that float across your laser beams isn't the safest thing to do. And so in this case, what you can see is actually this free OH gets broader and broader as you get colder and colder. And in fact, when we do fits to the data, this is the gray is your original data. When you do fits to the data, what you find is actually you start out with the free OH, which is up like this, and then you form a new peak that's like this, that's that with the SO2 bound. And then when you get down to 0 degrees, this one disappears, and it's all SO2 bond to the water surface. So that's what the temperature measurements tell us. So now the experiment results can only tell us so much. They say that SO2 is going to the surface, is kind of bonding there. But we'd like to know more. We'd like to know what that trajectory as it goes to the water surface looks like, how it orients, how it bonds once it gets there, and then also the answer to our multiple choice questions. So we'd like to be able to understand, for example, is it just SO2 with one water molecule? Because understanding this kind of chemistry, again, is important as we think about doing any kind of further atmospheric or climate modeling. So is there a bonding, lots of water molecules around the SO2, or what's going on? Okay, so here it is. So here's the calculations that we've done along with the SO2 experiments to provide further information. So what you see in the background is a lot of little water molecules, and I've only highlighted a few so you can keep your eye on that in order to answer this multiple choice question and figure out what's going on. So here we go. So the SO2, and we've got a little bit on these MD simulations, we've got a little string on that SO2 to gently pull it down, a little potential on it as we pull it down. Okay, and you can see it's taking its sweet time. Comes down, the sulfur atom tends to point towards the water. Let's see what those water molecules do. All right, then I go up and grab it. Okay, so then what we did was take that movie and snapshot and figure out what kind of clusters were there at the surface with the water coming around the SO2. And so what we find is actually, which is interesting to us because we'd like to be able to also compare it with gas phase work, is that this is now a histogram, the percent of SO2 coordination and then SO2 coordination in this direction. These are just different types of complexes that can form. Blue is cold, red is warmer. And as you can see, it's not just one SO2 bound to the free OH, it's actually clusters around that sulfur dioxide at the surface. But it's really impacting that very top layer, that free OH that is sitting there. And so you can see that it's these ring kind of structures that correlate well with what we know from gas phase measurements. All right, time to vote. So what role does a water surface play in gaseous uptake? And what I've shown you, you saw me show that SO2 comes down. The water tends to reorient itself around that SO2. You form different clusters that are there. Okay, so you ready to vote? I don't know. Here we go, okay? So, doorman, barrier, or temptress? How many people vote for doorman? Barrier. Temptress. Ooh. All right, you ready? There she is. That's a temptress. Okay. Went up and got the SO2 and pulled it in. Okay, now, I have to qualify this. So, as you know, I'm really concerned about women's issues, and I just showed you this picture of this very sexy lady up here, right? So I just want you to know that I went on the web to see what a male temptress looks like. Anybody know? If you went on the web, now don't look at your phone real quick. The equivalent of the male temptress is called the devil. And I didn't think the devil was really the kind of thing that would pull it in. So I'm thinking, you know, for me, I've been with this same guy, my husband, for over 40 years. So for me, what does a male temptress look like? There. I mean, that looks pretty good to me. That's my male temptress. But the point is that in this case, one of the first studies done like this ever was to be able to show that actually water takes an active role in yanking this SO2 in on this very molecular level. All right. Now what about CO2? You know, CO2, you leave your glass out at night, you wake up in the morning, you drink it, it tastes a little acidic, and we know that's because carbon dioxide goes in, absorbs, and makes that water a little acidic. But when we do the experiment, we never see this free OH broaden at all, so we know that the CO2 just dives right in. Doesn't stop at all, just dives right in and then forms the ions that are there, even if we go cold. But the difference of the thermodynamics are also very different for SO2 and CO2. So CO2 tends to come out of the water, not want to absorb as much when it goes cold, and SO2, it's the opposite. And could be due also to the linear nature versus the bent nature, but nevertheless, it's very different. Okay, I'm going to shift gears now to another environmental issue, and this has to do with environmental remediation. But it also has to do with what happens when you put oil on water. So oil on water has fascinated, or water next to hydrophobic surface has fascinated scientists for a long time, and that includes Benjamin Franklin. So Benjamin Franklin, when he would sail across the Atlantic, he was noticing that in his flotilla, that the water behind one of the ships in the flotilla had calmer seas than the other, and it turned out to be the cook's galley. So he was thinking, well, maybe it's because the cook's galley throws all the slop off the backside of the boat, and that might calm the seas. And in fact, sailors have known that for centuries, that you can by putting something oily on the seas, you can actually calm them around there. And in fact, he was so fascinated by what might happen when water is next to a hydrophobic surface or water next to oil, that he was known to walk through the British countryside with a cane and a little vial of oil on his cane. And then when he got to a pristine lake, he would pour that oil on the lake and see it spread. Of course, we would probably get arrested for that today, but in those days, he'd get away with it. But what he didn't do, though, was then do the calculation that Rayleigh did 100 years later to figure out the size of a molecule based on how far that monolayer had spread. But I think he's still a pretty smart guy. So why do we think about it these days, or how I think about it these days having to do with the environment, has to do with trying to understand some fundamental issues regarding how you can possibly work to remove an oil spill in a way that's safer than it is today. And let me explain what happens. We're not being able to solve it, but we're trying to understand the fundamental information that leads to some cleanup. So nowadays, if there's an oil spill, and they will continue to happen, unfortunately, what happens to clean it up is there are several different methods, one of which is to basically concentrate the oil with booms and then burn the oil off. And although you might think this would lead to a big fish fry, in actual fact, what it does is just burn that top layer of oil off. However, it also burns the booms, and the booms are very expensive. They're like links on a necklace, and each little link is about $500,000. But also look at the smoke that comes off. It's very toxic. It's extraordinarily toxic. And so that's not the best way to clean up the oil. So one of the other alternatives is then to disperse it. So in that case, what is done is to put some type of a soap or surfactant on the oil to break it up into tiny, tiny little droplets that then will go drop to the bottom of the ocean or will be washed away, making these tiny little emulsion droplets. And so in this case, what's happened is that you've got this dispersant, such as a soap, long oily tail, and a polar head group. This surfactant or these dispersants are stabilizing this droplet long enough for them to go away. Now, unfortunately, today, there is no safe dispersant to be used that's effective. And in fact, what is used is something called Corexit. And this is actually not just one surfactant, but it's a whole mixture of different surfactants and chemicals. And it is used as a dispersant to disperse the oil. It has some safe components, it has some not so safe components, but when mixed together, it's toxic. So that when people are going out to clean up and the dispersant has been applied, many people get sick trying to clean up the birds and so forth, as much due to the dispersant as the oil. So the holy grail is to figure out how to develop a safe dispersant that can be used in a variety of different conditions, because if you're cleaning up an oil spill in the Prince William Sound versus the Gulf, temperature is different, and also the viscosity of the oil can be different. But this Corexit seems to be able to disperse a lot of it. But again, the holy grail is to figure out what you can possibly use as a safe surfactant. And so what we're not determining the safe surfactant, we're going back to figure out what's going on at that oil-water interface so that we can understand what stabilizes, what basically factors go into stabilizing this guy at an oil-water interface. Okay, so let's do a little bit of the background. So what happens that we've learned when you put oil on top of water? And in this case, we're doing a similar experiment, but now the interface doesn't have air above it, it now has oil. And so now this is a spectrum. You do the same spectrum as before. And the black is now the air-water spectrum that I showed you before. And this time I've written down the frequency of that free OH. And look what happens with the oil-water. Look, it's shifted. So many of you have probably heard oil and water hate each other. And in fact, if you go into many of the biochemistry texts, they would say that when water gets next to some membranes, it balls up like a clathrate and doesn't want anything to do with the oil. But in actual fact, this shift in the free OH has told us that actually water bonds weakly to the oil. Very weak dispersive type force. However, that's important because that then stabilizes the interface and actually creates a dipole there that helps pull things to that, small dipole helps pull things to that junction. So that was new in itself. And in fact, it's not just this, in this case, this was carbon tet, but it also is, you can find this for hexadecane, you can find this for fluorinated. So the strength of this, the amount of this shift is there's less of a shift with fluorinated, then it becomes then alkanes, and then a little bit more of a shift with carbon tet, which is polarizable. Put a little bit more polarity in there, but you continue to see this shift in the free OH or this bonding until you get to where they're soluble in one another. So that's been a really important marker for us to be able to say that this bonding interaction is there. Equally important, though, for this oil-water interface is this interface is extraordinarily clean. So if you have any impurities at all in the water or the oil, they will go to the interface and this whole spectrum will completely change. When you have impurities, that free OH goes away. It's gone because everything grabs onto it, and then what you get instead is a spectrum that looks like this, where the water modes that are strongly bonded show up. Okay, so that's what we get when we make this, and we've done a whole series of different experiments as we did with the air-water, but I just wanted to give you a snapshot of this. So it weakly bonds, in summary, it weakly bonds to this oil. So that's a starting point with regards to trying to understand this interaction. So then, different than the air-water, although quite similar, this is an oil-water interface. What we've learned with the simulations as well as with the experiment is there's a weak bonding interaction between the nonpolar film or oil. And then you have a high degree, again, of this molecular ordering at the interface. Got these guys, again, straddling the interface and others which are highly oriented in the plane. And so what this is now this scale with regards to that I mentioned just a moment ago, and this is to show that we've been able to do it on a whole different other set of hydrophobic surfaces from a fluorinated film and films, not just liquids, but also films, hydrocarbon films, carbon tet, and then also on. So another thing that we study, which is, which I'm going to get to too, I just want to say we not only studied that oil-water interface, but now we look to see what happens when soaps go there. So now we're just looking at the water, but we're also looking at the head group modes of this surfactant. It could be sulfate, could be different types of polar head groups, sulfonate and so forth, and see what happens to the head group as well as the tail as they go to the interface. And so, we know that these surfactants, they love to go to this interface. They're really very happy there because they've got their head group, a little schizophrenic, they got their head group in the water and their tails into the oil. And what we found then by doing spectroscopic measurements of the ordering of the tails as well as the solvation of the head group, the most important thing that we've learned from these studies for these simple surfactants on a planar surface are that, for example, when the tails are nicely ordered, the surface tension plummets. But when the tails are all disaggregated and not nicely ordered, there's little change in surface tension at all. So you can have the soap there, but there's got to be this hydrophobic interaction between the chains in order for it really have its effect. Its effect to be a good detergent, its effect to be a good dispersant also. Okay, so that as background, now our most recent studies over the last several months have taken these oil-water experiments to another level. And that is to be able to now be able to study the surface of an emulsion, oil in water, and study its surface when it's on a round surface as opposed to a planar surface. And so in these studies, what we're doing is this case, we're doing nanoemulsions size of 200 nanometers. And in this case, this is just simply the emulsion and then putting the laser beams through. And in this case, rather than reflecting it off, we're scattering the light comes off in a scattering angle, and then we collect the some frequency light at the scattering angle and still tune the infrared beam. And so for these studies, we've been using hexadecane as the oil. And this is a surfactant. We've been sticking with AOT because it's a common surfactant. It's been studied for my cells as opposed to these nanomulsions, but it's also a component of Corexit. It's the safe one because it's actually in your ice cream too, so we hope that's safe. So the AOT is actually used as a surfactant to stabilize these nanomulsions, and so we've been doing studies, the first studies of this kind, to be able to do AOT, to be able to look at how it assembles at the interface. And so what we found, for example, is that the AOT goes readily to this interface. It forms these nanomulsions, and then we can study its structure as it stabilizes. And so what we've learned from that, compared to the planar versus the round, and a main point of this to compare with the planar versus the round is not just to see the effect of, how's it going to assemble at a round surface, but it's more the case when you're at a flat surface, you don't have to do anything there's no stabilizing going on, there's just absorption. So the molecules don't have to do something other than to go there. But with an emulsion, they've got to stabilize the surface. They're acting to stabilize that nanomulsion surface. And so in that case, being able to compare the planar versus the round helps us to understand what factors go into stabilization. And so the difference that we find in doing the spectroscopy of both the head group and the tails is that actually what's going on with the nanomulsion surface, and these are big. I mean, I have my hands like this, but these nanomulsions are big. So also the question was, when is the Earth flat? So when does planar, and in this case, the nanomulsions are so large that actually, if you were on the surface and the size of a surfactant, you wouldn't see so much of the curvature, just like if we were going outside, if you still believe the Earth is round. So, which I do. But what we find is that the tails actually are much more disordered for the nanomulsion than at the planar surface. So that tells us that the tails, how they orient, how they change, how they are at the surface, actually could be helping to stabilize. I'm going to take this one step further in this last slide. The next step we took with this was that we wanted to understand what happens if you take the surfactants away. So there have been recent studies that have suggested that you can actually make nanomulsions without a surfactant, and they'll be stable. However, they have a high negative charge when you do that on them. And so there's been hypotheses that the negative charge is due to hydroxide going to that interface, and there's been a lot of discussion about that. There's also a suggestion that it's possible that in these bare nanomulsion studies that there could be some contaminants there, and those contaminants, like the surfactants, are going to the interface and stabilizing it, and could be negatively charged surfactants that's there. So I've been really curious about these bare nanomulsions because of the fact I wanted to know, is there a free OH at the nanomulsion surface? Because that would tell us at a bare nanomulsion surface, because that would say the surface is not stabilized by surfactants at all, but actually just can form it without surfactants or a minimum. And so in these experiments, the other experiments are hard. These experiments are particularly difficult, doing some due duration studies. So I'm very proud of the students that they did it, looking to see if there's a free OH, like there is at the planar interface, because that would be an indicator also of whether the water is bonding more strongly to the oil at these surfaces. And that's what we did. And sure enough, even though previous studies had said there's no free OH, we find the free OH is there, and it's shifted even further. So that actually a nanomulsion with very little, if anything, surfactant to stabilize at the surface actually binds more strongly to water than at a planar interface. So it could also be contributing to this stabilization. So that's been really cool to see, and we also been able to show that if you add, and there's, what I should also say, is these nanomulsions that we've been able to create with the free OH have almost zero negative charge on them. So again, and so what we can do is we can add small amounts of surfactants, trace contaminants, and reproduce what has been done in the previous studies. Now that's not to say the previous studies should be trashed at all, because they might have some impurities there. Science is a process and understanding further and improving with time. And so we're excited to be able to be part of that process. So, to summarize, I've told you about the kind of studies that we've been doing to give you a glimpse of the kind of challenges that we're trying to attack, but also the challenges that lie ahead. I told you about sulfur dioxide, how it interacts with the water surface in a new way, and also how carbon dioxide dumps in. So in that case, I guess you could say it sinks in and swims, and also maybe does a little bit of surfing, but more of the surfing happens with the surfactants surfing on the surface, and then talk to you about our recent studies having to do with extending these to nanoemulsions. So with that, let me thank the students. This is, of course, in the water fountain. Where else would we be wanting to take a group picture and having some fun? Nobody actually fell in, even though it looks like everybody's going in. But I must say this group, Teresa Tarbuck, Stephanie Oda, and also Eric Chamet, were the ones that did a lot of the SO2 work, and Eric was really responsible for the SO2, a lot of the calculations. Eric then has gone on to work at Microsoft. Stephanie is teaching high school outside of Portland, and Teresa is teaching at university. And then the gang up here, there's Fred Moore, faculty member from Whitman, that comes to visit us quite frequently in the summer for his sabbatical. And Nick Valley, who is here, done a lot of the calculations. It's really hard to see all these faces. This light green guy up here, he's done the nanoemulsion studies. And then Regina, who's done the oil water studies, and also several of the other in the group. It's hard to see. But I want to show one last slide because the Dickson Prize, which I'm very honored to be receiving, is really not about just these students, but also a large group of students that I've had the pleasure and privilege to work with over the years at Oregon. And you'll notice a few of these are, as a Halloween costume. We have a few traditions in our lab, and that's to dress up for Halloween every year, and there usually is some kind of a theme. One year it was farm animals, and I missed the memo and wore a Heinz ketchup costume instead. And David Bowie was another one. Anyway, and the other tradition is that when you pass your thesis or you get tenure, you get a pie in the face, or you forget to tell us when your birthday is, or any other reason. So we have most people just have paint on the walls. We have pies. But anyway, it's a fun group to be with. So I thank them, and I thank all of you. I'm so honored to get this prize. Thank you. Oh, I had my share when I got tenure, and then a few more after that. See, when you get somebody with a pie, it's completely legal to pick the pie off the ground and give it to the next person.
Okay.
Multiple scattering events.
So Jerry asked us some questions. Now we can return the favor. Does anybody have a question? Okay.
Yeah. Oh, there's a microphone, yeah. Are you doing any work with PFAS? There's a lot of challenges now with the water-air interface and the perfluorinated compounds, AFFF. I know up the road, I'm an Oregon Duck, so I want to see Oregon do better there. Because up Oregon State, Jennifer Fields is doing a lot of chemistry work on PFAS compounds. Is that something you might be looking at in some of your research?
Yeah, so we did a lot of the fluorinated work earlier when we were doing the initial oil water studies, but we haven't done so much beyond that. So no, not very much now. We just got sidetracked. You know how that goes. Yeah.
Questions in the audience?
Thank you. I would like to know if you have done any study using your spectroscopy on pathogens, including the one we see in the news every day now.
Sorry, I didn't quite get the question. Did you get the
Have you done any studies on pathogens? Did I get that right?
On pathogens?
Yes.
No. Scares me to death. Yeah. No, just much simpler. We have done some work in the biochemistry area. We've done quite a bit with phospholipids and looking at phospholipid layers, but that's as far as we've gone. For anyone that asks anything about biology, I just want you to know anything that grows scares me to death. So you are all more courageous than I.
A question over there? Oh, he's behind you.
Hi, I was wondering about the studies you showed on the droplet versus the planar interface. How much does curvature matter? what curvature do you start to see that shift? And is it dependent on the curvature?
So what we did, because we have kind of we do have a limitation on how small we can go with this technique, and that's about 100 nanometers. So what we did was we took AOT and we looked to see if it changed between 100 and 800 nanometers, if the spectroscopy changed at all, and there was absolutely no change whatsoever. So I think we're really in the realm of the curvature doesn't matter. It's more the stability. So the curvature just, I think you have to get more down towards the micellar region to where it's going to make a difference. But again, the other difference, and I want to point this out, and that is with these nanoemulsions. I think we talked a bit about it when we were together. With these nanoemulsions, you don't just shake it up like salad dressing to make an emulsion. In this case, you actually have to sonicate it. So you put a lot of energy into that nanoemulsion, and that state, it's in a metastable state. So it's in a kinetically stable state, waiting to go down to its thermodynamic state. And so thinking about, is the curvature, I think we have to say no curvature, but I'm really curious about how the energetics in that kinetically stable state might make the molecules orient differently than when they go thermodynamic. And the thermodynamic, of course, would be the planar. So now that we can get rid of the curvature issue, we can focus as much on the energetics. David?
Hi. During the Deepwater Horizon oil spill, eventually what was done was to inject surfactant directly into the oil emitting at the ocean bottom. So it's a pretty complex environment here. We have hot oil coming out in pretty cold water, and the aim was to keep the oil dispersed at depth. And it was pretty successful, but the chemistry of it's pretty complicated. From your studies, what would you surmise is going on there? It's the surfactants becoming directly affiliated with the oil immediately upon release, hot oil in a cold water environment.
So I think, first of all, I think the way we're going to have to figure this out has to do with some kind of modeling, because it's so complex. And because, for the Gulf Horizon spill, it went on for so long, and the density of the oil changed with time, as I believe, too. And so the effectiveness of different surfactants, different kinds of surfactants, changes not only with temperature, but also with the viscosity of the oil and the aging, right? If the oil is 12 hours old on the top of the water, it's much thicker, and so breaking it up is hard, too. So I think I can't say, for our studies, all we can do is say, is try to learn about, now as we try different types of surfactants there, what factors go into stabilizing so you can have more predictive power. But it's hard for me to go that much step further. I'd have to defer to others that actually get in there and do the kinds of things that you're talking about, which is in these very salty, brackish waters, cold temperatures and so forth. But the thing, when I spoke at one of the Gulf Coast remediation meetings a couple of years ago, what struck me was and I was asked by a woman by the name of Rita Caldwell to come speak, because she felt that the basic science was just really missing in all of this. And it was amazing, because that was really true. So I think we just need, people were coming up afterwards. They'd never thought of, most of them were working more, cleanup and larger levels. Very few of them really thought on the molecular level. So I'm hoping that we can contribute in some way, but we also know it's a pretty simplistic system as we're working with now.
One final question, Hyun? Over here.
Hi, as a computational chemist doing MD simulations, your results are very, very interesting. So a question regarding the interface between oil and water. Mm-hmm. So at the molecular level, since I'm doing MD simulations, it's sort of, the interface is not that smooth, right? So
that's right.
Very, very rough.
Right.
So I don't know whether this dangling OH, how they look like, and also how the oil orientation. I don't know what molecule you use, like
carbon tet or hexane. Okay. Carbon tet's the easiest because we can get the infrared.
Yeah, carbon tet is symmetric, so yeah.
Yeah.
But how the oil molecules will look like at the interface.
Yeah. So interestingly, that's a great question. Thanks for asking that, because we average out. You've got waves going on and you've got the roughness, and we average that out because we're not taking a single snapshot. So it actually averages out. It's really remarkable, and even that interface tends to be more stable in terms of the spectroscopy than the air water. But it's interesting because for this particular, so yes, so the 3OH is still there, but it's there on the average. And you know it's not just like this, it's kind of bobbing around too, but we know that it just has very weak interaction between the two. What we pick up in the oil-water studies, which I didn't talk about, is that we also see water monomers then that go into the oil. So we can, it's hard to pick that up in vapor water because they just go away. But the spectrum it actually looked quite different for the oil. It went up and then it didn't have a big dip in it. And that's because they're water molecules that are highly oriented into the oil. And the dielectric is such that the field from that the dipole nature of that interface. That field penetrates about 17 or 18 angstroms into the oil. And in fact, the carbon tet, when you do the simulations, the carbon tet is actually oriented also to that dimension. And so that then gives us this kind of intensity that you may have noticed, that it's not just, things are still going back and forth. Things are still going, and you've got some of the carbon tet that goes into the water also.
I'd like to thank Jerry again.
Oh, thank you. Yeah, thank you.
Thanks for being such an interactive audience.